Ever wonder why we don't see literal ghosts of ourselves existing in two places at once? Even though the rules of physics say it should be possible. In the mind-bending quantum world, tiny particles happily exist in weird states like superposition, being everywhere and every state simultaneously. But when we look at big things like apples or people, they always seem to be in just one definite location, right? So, what actually bridges the gap between that fuzzy quantum reality and our crisp, solid, everyday experience? The scientific explanation points directly to a crucial phenomenon that scientists call quantum decoherence. Decoherence happens because even the smallest macroscopic object is constantly bombarded by countless environmental particles, like stray photons and air molecules. Each tiny collision forces the quantum system to interact with its surroundings, effectively becoming entangled with everything around it. This entanglement acts like information about the particle's superposition is constantly leaking out into the vast, messy, noisy environment. The delicate, complex wave function that describes the superposition instantly starts to look like a much simpler, single, definite wave function. This process happens incredibly fast, virtually instantaneously, the moment the object gets even slightly larger than an atom. It is kind of like trying to keep a single drop of colored dye perfectly mixed and isolated in a giant, constantly churning swimming pool. The environment essentially performs an uncontrollable, continuous measurement on the quantum system, without us even needing to look directly at it, because all those potential states are now correlated with the environment. The ability for the object to exist in multiple states completely vanishes for us observers. That is why the world we observe looks so classical, solid, and perfectly predictable every single time we interact with it. Decoherence is the powerful mechanism that rapidly washes away all the weird, fuzzy quantum behaviors on a large scale. Ultimately, it's the crucial reason the rules of the very small don't seem to directly apply to the very large world we inhabit.